Welcome to Ask and Learn.
In this problem, we have a bar that is pivoted at its left end. At its right end, it's attached to a spring whose other end is on a roller so that it can slide horizontally and allow this force to remain in the vertical direction. Otherwise, the geometry would get pretty ugly here. The bar has a weight hanging from it at its mid-length, and then there's an applied moment acting on the bar. Now, we're asked, let's see here, we're asked for the angle, for basically this angle that the bar will deflect, given the loads that are acting on it. So we have our reaction force at the pivot, the pin joint, and I'm going to call that my origin. The spring force is over here, and it's in the vertical direction. This position is a distance L from the pivot in this direction here. The weight has a force that acts vertically, and it's halfway along the length of the bar. And then we have the applied moment. And as I've drawn it, that would be a negative moment. So we can sum forces and set them equal to 0 and sum moments, and remember to include our applied moment and set that equal to 0. Now, the spring force is given by minus k times y2, and y2 is just L minus sine theta. And so it's a minus because we have a spring force on this. The force on the spring is going to be down, and we're measuring positive up. So a negative force would create a positive displacement. So we have this negative sign here. And in the end, really all we need is this moment equation, because we're not asked to determine what these reaction forces are. So just this moment equation is going to give us an equation for in terms of our parameters and theta. Okay, so it's not a simple function of theta, and it's not something we can really solve by hand. But we're given values for all the other parameters, so we can plot. We can move all these to the one side and make this a function of theta and plot it. So we plot y of theta equals LW plus 2m for secant theta minus 2kl squared sine theta. So we plot that, and we see where it goes to 0, and those would be solutions of that would be values of theta that will solve this equation. So we do that, and I just plotted it for theta goes from 0 to 2 pi. And so what we can see is that we have actually 4 solutions in this region, and we can use numerical root finding or just trial and error to figure out where these points are. And this is in radians here, but I converted our answers to degrees. This point is at 23.2 degrees. Here we're at 85.2 degrees. Here we're at 164 degrees. And here we're at 268 degrees. Now, what those solutions look like, one is kind of down, like kind of as it's drawn in the book. One is close to a right angle, so almost completely vertical with the spring, the spring force almost directly aligned with the axis of the bar. This one is very close to kind of being close to being 2 pi, so 180 degrees away. And then this one is kind of close to being, let's see here, uh, you know, basically up this way. So we have 268 degrees. Now, what you can look at is whether these solutions, they didn't ask us, but some of these solutions actually aren't stable. Um, and we could check that using a little more analysis. But you kind of look at it by the slopes of these curves as they cross the line, because you can think of this slope as a stiffness. Just like if you plot f as a function of x, and you get a line, and the slope is the spring constant. You can think of this as a stiffness, and basically a torsional stiffness. And if depending on the slope, if you have a stiffness, which basically if you move it more, it then wants to move even farther, then you have an unstable system. So these are the solutions, but some of them will be unstable.